Alright, the next one we're gonna do is number, where is it? I just saw it. 34. X times log of x. Let's call it f x times natural log of x. So of course we're not doing absolute values here, as you might see, so this is only defined for positive values of x because of the log component. So I see that there is a logarithmic function, I'll call it a log component, which means the function's not going to be defined everywhere. I could have vertical asymptotes, we will have to see. Can I find a y-intercept? Well, for that I need to plug in x equal to 0, and that is not gonna go well, so none. Alright, so we go ahead and see if we have any asymptotes. Asymptotic behavior, rather, which is just a fancy word for find some asymptotes. So I look at my function, and I see, well, what happens? I have to ask, in general, what happens when x gets really big, positive and negative, but in this case there is no negative side to speak of. So, x times natural log of x. Now, what is the form of this limit? The form of the limit is, well, x goes to infinity, and log of x, I remember the shape, also goes to infinity. It's a little slower, but still. So I have two large positive numbers, so large and positive. So some of these limits are, or can be, quite straightforward. And so I have no horizontal asymptotes. It makes no sense to look at the left side, there's nothing there. What about vertical asymptotes? Well, I know that for the log function on its own, I have a vertical asymptote at x equal to 0. But the presence of this x might change things a little bit. So I want to check if x gets close to 0 from the right, what is happening to the function? Does it still go to infinity, plus or minus? This is a little bit more complicated than just checking in a rational function for a 0 denominator. What is the form of this limit? Well, x goes to 0, and log of x goes to infinity. Now, this isn't a number, so it's really a question of how fast these go. If the first part goes to 0 super fast, relatively speaking, it can control the whole change in the function, and the whole thing can go to 0. But if the second part grows fast before the first part can shrink, the whole thing can blow up. So very similar to 0 over 0 or infinity over infinity, anything can happen. So what I want to do is I want to rewrite this so that it looks like a fraction. So I'm going to put the log of x over 1 over x. Then division by a fraction is multiplication by the reciprocal, and I get my original function again. So I'm just going to do it up here. What is the form of this limit? Now the log function goes to negative infinity as x gets close to 0, and the bottom 1 over x also goes to infinity when x gets close to 0. I don't care about the plus or minus. If it's infinity over infinity, I can use L'Hopital's rule. to see how does this thing really behave, to be absolutely sure. Now, the derivative of log of x is 1 over x. The derivative of 1 over x, remember this is negative x, not negative x, doing the derivative, x to the negative 1, which has as derivative negative x to the negative 2, like so. If I now simplify this a little bit, and I cancel the x's, or this goes up at the top and get multiplied by x squared over 1, negative of course, then I see this simplifies to negative x. And as x gets close to 0, this gets close to 0. Yeah, from the left, but I don't really care that much, to be honest. But sure, you can indicate it from the left. What does that mean in terms of my vertical asymptote question? No vertical asymptote. I have to get an infinity or plus or minus. There are no vertical asymptotes. So yes, the presence of the log function does make things a little bit more complicated. Just remember that 0 times infinity is also a little bit of a problem where I can't be sure what happens. It depends on the pieces. So this being 0 actually means that x goes to 0 faster than log of x goes to infinity. So it can dominate and control and shrink the whole thing. So as a result, I can not put anything on my graph. I can make a graph, but I don't have a y-intercept. I don't have asymptotes. I kind of have nothing at this point. Not the start I was hoping for, but there it is. Nothing. Maybe step 3 will shed some light on this, where I'm looking for increasing or decreasing behavior. There I'm going to look for the derivative, and my original function, remember, is quite straightforward. I'm going to use the product rule, derivative of the first times the second plus the first times the derivative of the second. Let's clean this up a little bit. I'm just going to write this, which simplifies to 1, at the front, so I don't get confused. If I write log of x plus 1, I get confused. Is it this? Is it this? What's inside the log? So to avoid confusion, I just reorder them, and I never read this incorrectly. So there's my derivative. Super easy. Now I still check backwards, like this. When is this derivative equal to 0? Well, I'm gonna be able to find that by setting it equal to 0. That means that log of x equals negative 1. And if I rewrite this to the exponential version of the equation, I get e to the negative 1 equals x. So in other words, x equals 1 over e. Alright, now we have something, and oh, my little curly bracket here was a little premature. The other check I do have to make is when is the derivative undefined. In addition, of course, to the basic domain where the valid x values are. Outside of that, I'll say here, no additional x values. There's nothing extra that I'm getting out of this. I know there's a log component, so having anything 0 or negative makes no sense. So I will make my table over here, and I'm only splitting it at 1 over e. I have one piece, and it gives me my derivative. This piece, 1 plus log of x, is 0. We've established when x is 1 over e, it is the derivative, so it makes it 0. Now you can plug in little representative numbers here. You can't plug in 0, but 1 over e, let's see, what is 1 over e in case you are curious. 1 divided by e is 0.36-ish. 0.3679. So plug in a 0.1, plug in a 0.5, see what you get. You'll get a negative and a positive, which is then the same for the derivative. Then I have a negative slope, I have a horizontal, and I have a positive. So it shows the cup shape that is happening. We can write our sentences. F is increasing on 1 over e to infinity. Should I include 1 over e? Do I have a y value when I plug in 1 over e? Yes, I definitely do. And f is decreasing on negative infinity to 1 over e. Don't do this out of habit. There is no left side here, remember? We should maybe clarify that by saying here undefined when x is negative or less than or equal to 0 because of this log component. So as a reminder, it might be beneficial to put a little 0 here and say bad things are happening undefined. So then when you see it there, it reminds you, oh, I can't do this. It can only start at 0, and I can't include 0 either because of the log. So maybe that helps a little bit. Is this a critical point? Yes, it is, because it comes out of my check, and there's a point. There is a function value. So finally I have something to put in my graph. I have something interesting happening at 0 in that there's only a graph past that. I am finding something at 1 over e, and that something is, did we find a y value? We did not. We probably should. So let's say up here, if x is 1 over e, then y is f of that, and my function is x times log of x. So 1 over e times log of 1 over e. That's going to, well, this guy is negative 1, so it's negative 1 over e. So negative point, what did we say? 3679. So that's going to sit down here, negative 1 over e. And I know it's coming down. Let's just do the right side first. I know I'm going up to infinity because we found that over here. But what happens when I get close to 0? I'm going to head to 0 from the left, from below negative numbers. So I'm going to head towards 0 like this. But if I go left to right, that confirms I am decreasing. Sorry, this negative is very close here. I'm decreasing, turning my little cup. Let's do the little cup. There we go. And then increasing. So the shape is sort of starting to take shape. Please remember to click the like button if you enjoyed the video, and to subscribe if you want to be notified of more videos.